Yeah, thank you very much. Thanks for coming. Yeah, I'd like to tell you about Gram matrices. Before we're doing, this is the logo for the ERC Synergy project that Johannes and I and others are involved in. That's called Positive Geometry in Particle Physics and Cosmology. And so these three cartoons are for positive geometry, particle physics, and cosmology. And today, towards the end, I'll say a little bit about the cosmology. So the lecture today is based on this article called Gram Matrices for Isotropic Vectors with Jesus and Swala. And I'd like to start the lecture with the puzzle. I'd like to welcome you to a puzzle. And the puzzle goes like this. Let's look at a 4x4 symmetric matrix with 0 entries on the diagonal. There are 6 parameters in this matrix, A, B, C, D, F. And we could maybe wonder what could be the rank of such a matrix. Well, this matrix could have rank 4 if these A, B, C, D, F are generic. It could have rank 3 too if the determinant vanishes. It could have rank 0, right, if all the parameters are 0. It cannot have rank 1. As soon as one of the entries is not 1, there's a 2x2 non-vanishing minor. But the interesting case is rank 2. So my quiz for you is, what are all the matrices like this that have rank 2? So can you describe this set, variety, space of matrices like this that have rank 2? And see, we only have 20 slides today. So maybe we can throw this in the room. What do we think about this? What question should we even ask about such a set? Well, the question would be, what is the dimension? How many degrees of freedom do you have in making a rank 2 matrix? I mean, for example, if A is 1 and everybody else is 0, then that would be a rank 1 matrix, but maybe there are more free parameters to choose. Okay? So this will be a theme of this lecture, this kind of thing, and we're going to get back to it. Let me start the tale with 6 vectors that live in an R-dimensional real vector space. My vectors are going to be called P1, W1, P2, W2, P3, and W3. And I would like the vectors to satisfy the following equations. So Pi dotted with itself is 0, Wi dotted with itself is 0, and then if they have the same index, Pi dot W is also equal to 0. Now the dot refers to a quadratic form given by a symmetric R by R matrix Q. And if I have a vector that dots to 0 with itself, in the math literature, we're saying the vector is isotropic. But here I have a sort of this joint isotropic, a stronger assumption. So the vectors themselves are isotropic, but I also have that Pi is perpendicular to Wi. Now in physics today, well, we're going to have space-time again, but if it's 4-dimensional, so in a 1 plus 3-dimensional space-time, then the quadratic form would be given by this diagonal matrix with -1 and then all ones, let's say, on the diagonal. And these 3 pairs of vectors represent 3 massless particles. But today we have, as yesterday, the momentum vector Pi, but there is a second vector called the polarization vector Wi. So for each I, there's a momentum vector Pi and a polarization vector. Well, and these conditions here says, in particular, the first and the last say that both Pi and Wi lie on the boundary of the light cone. They dot to 0. Okay, now what's going to happen in this lecture is we're going to work our way up through 4 different coordinate systems. And this is going to be important. So progressively, the coordinate systems will become more invariant. more physical, and at least to me, more complicated. Now, the second level is we'd like to look at quantities that are invariant under the special orthogonal group, and those are the entries of the Gram matrix. So in our little example, we're going to write the Gram matrix. That's the one that records the pairwise inner products. So I can write this like this. I have this matrix that's a 6 by R matrix. And here in the middle, I have the R by R symmetric matrix for the quadratic form. And finally, here the transpose, that's an R by 6 matrix. And this matrix, if you multiply it out, it will look like this. It will have a 0, 2 by 2 blocks along the diagonal. That's this hypothesis, right? And then the other entries are some entries xij that I don't know. Right? These are the non-zero inner products between p's and w's. So I have 12 parameters here. But maybe, very first question is, what do we think the rank of this matrix is? So I look at this 6 by 6 matrix. So maybe Matthias, what do we know about the rank of this matrix? Know anything? Felix, any opinion about the rank of this matrix? Not clear? Let's say R, if R were 4, what would you think would the rank of this matrix be? So we say this again. This is a 6 by 4 matrix times a 4 by 4 matrix times a 4 by 6 matrix. Right? So what do we think the rank would be of this 6 by 6 matrix? At most 4, right? That's what people call a low rank factorization. So if R is less than 6, the rank can be at most R, right? Because in the middle we have this R by R matrix, and we cannot go beyond the size of the middle matrix. Very good. So this Gram matrix has rank at most R. So now let's do the same experiment that I proposed yesterday. Let's take this variety. This variety just walked into the door. So let's study this variety. Right? So in computer algebra, we would now set this up. We would fix a polynomial ring in 12 variables, xij, these 12 things. And we would look at the condition that the rank of this matrix is at most R. Right? What are the matrices like this that had rank at most R? Well, to communicate this to our computer, we would specify the ideal of R plus 1 times R plus 1 minors. And we would ask, what is this variety? And I'm looking at this variety maybe in the affine 12-dimensional space. The question is, what is the variety given by the minors of a given size of this matrix? Please interrupt me if there's questions. So I'll show you what happens when you perform this experiment. And sorry, Lizzie, we're going to do this in affine space just to keep it a little simple here. Okay, what I'd like to do is I like to forget where this came from. The question is just like the quiz. Okay, the quiz was, whoops, now I don't know how to do this. Maybe I do. Full screen. So it's the same question as in the quiz, right? So in the quiz, we asked this matrix, how can this matrix have rank 2? Nicholas looks so happy, he maybe figured out already what this variety is, right? And it's the same question, right? The same question as now, let's look at a matrix like this with unknown entries xij, and what is the variety of matrices of rank at most R? And R is an integer between 0 and 6. Question clear? So you can do this on your own, right? So Ayush could now take his computer algebra system, whatever they use in RISC-LINS, type in this matrix, or you could hold your phone and say, Claude, determinantal varieties. Tell me about these determinantal varieties. Okay, so that's what we're going to do now. All right. Well, of course, I like to use Macaulay too, or some people like to use Oscar. There are merits, of course, to using Mathematica, but I think it's good for physicists to know that in mathematics there are also other computer algebra systems, and so these are the ones that maybe we could try out. Okay, so Ideals Variety Algorithms is the name of an undergraduate textbook in algebraic geometry that's good to be familiar with. So we're going to use Gröbner bases to explore this. And we're going to work our way up from rank 0. So what is the ideal? What can we say about the ideal of 1 by 1 minors of our matrix? Well, this ideal contains the 12 variables, so the variety is just the origin, right? So there's only one solution, that's the 0 matrix, and the 0 matrix is 1 point. That's a 0-dimensional irreducible variety called a point. Well, let's go to rank 1. So that's a little more interesting. So now I'm taking the 2 by 2 minors of this matrix, and I say, what happens if the 2 by 2 minors are 0? Well, it turns out the variety is still just the origin. But now, so it's only the 0 matrix, but now this solution has multiplicity, has higher multiplicity. Higher multiplicity, it has multiplicity 13, but the dimension is still 0. So now this ideal is not a radical ideal. It is not a prime ideal. It is a primary ideal, and it has multiplicity 13. So you have a fat point of multiplicity 13. Let's look at rank 2. So now we're going to look at the 3 by 3 minors of my matrix. And now you find that the variety has 3 irreducible components. Each of these irreducible components is a 5-dimensional irreducible variety. So algebraically speaking, there are 3 minimal primes. But there are also 4 embedded primes, right? You have these 3 irreducible components. But where these components come together, there's a non-reduced scheme structure. There's some chunky stuff happening where they intersect. Now, as we go on here on this slide, we see nouns in red. And in a moment, we're going to see adjectives in blue. Right? And that's how it goes, right? In commutative algebra, we're studying red nouns and blue adjectives. And Lorenzo, this stuff is supposed to be easier than the spinner brackets yesterday. Very familiar to those who take an algebra course. Let's get to some blue adjectives. So if R is 3, now we're looking at the 4 by 4 minus, the 4 by 4 subdeterminants. So this is an interesting case. So now the variety is toric. That is to say, the radical is generated by binomials. So if we're carrying out the symmetry Lie algebra calculation that Nicholas asked about yesterday, would find there's an algebraic torus as a symmetry group. So the variety is irreducible. The ideal is primary, but it's not radical, therefore not prime. But this toric variety is dimension 6. Right? You can see the dimension goes up, right? As we increase the rank of the matrix, we get more and more matrices. Now let's look at the 5 by 5 minus. That's an interesting case, right? Because now we're in rank 4, so that's the dimension of the space around us, physically most relevant. Now the ideal is radical, but it's not prime. It has one main component and 3 others. There are 4 components, one that we're going to be particularly interested in, and they're all 9-dimensional inside our ambient 12-dimensional space. And last but not least, well, R equals 5, so there's just the determinant, right? So the determinant generates a principal ideal. It's an irreducible polynomial here, so it's a principal prime ideal. So it's a hypercircle that has dimension 11 in a 12-dimensional space. Okay, so this is a very simple, and now that's the first thing an algebra person would do, right? What are all the different strata that we can have for the rank? So again, there's a subject that you can take a course in and read yellow books called commutative algebra. And commutative algebra is the study of red nouns and blue adjectives. Are there any questions? This is just an experiment. So, okay. So what you're supposed to take away from this is sort of an erratic behavior, right? So many different kind of phenomena can happen. And it's not so easy. When you look at these minors, many different structures you can have and need lots of blue and red words from textbooks. Let me maybe talk about this main component a little bit and show you a picture. So here we had this R equals 4 case, right? So in the R equals 4 case, we are looking at matrices like this of rank 4. So let us find a parametric representation in algebra language, or let's make the rank 4 manifest in physics language by writing down the low rank factorization. Right? So this matrix having rank 4 says I can factor it as a 6 by 4 matrix times my quadratic form times this one here. Just to match the picture, I changed the quadratic form to be 1, 1, minus 1, minus 1. So I Vic rotated myself into a situation that the picture looks a little bit better. All right. Well, what's happening here? Let's look at these row vectors. So these are rows A, B, C, D, E, and F. So these are 6 points in projective three-dimensional space. Okay. Now let's look at the line spanned by A and B. So the line AB, so A and B span a line, CD span a line, and EF span a line. So the 3 pairs of row vectors span a line in 3 space. Now the condition here, the 0 condition, says that these 3 lines lie on the quadratic surface defined by the quadratic form. Right? The entry here says that A times A is 0, so the A point is in the yellow surface. The B point is on the yellow surface, but the crosswise 0 says the entire line has to be on the surface. Right? So the AB line is on the yellow surface, the CD line is on the yellow surface, and the EF line also is on the yellow surface. Now, how can these 3 lines be on a surface? Well, this quadratic surface has 2 rulings. Every quadratic surface has 2 rulings, and here it's real visible, by this most real friendly, like in Melissa's talk is very real friendly. So to show the most real structure, I chose this. Now, how can 3 lines be on the surface? Well, there are the blue lines. That's one ruling. There's the red lines. That's the other ruling. Well, either they all have the same color, or 2 have one color and then the other color. But because they are labeled, there are 4 irreducible components. So the main component is if the 3 lines have the same color. That's the main component. And then the other 3 components are red, red, blue, or red, blue, red, and so on. Okay? Very good. So I'm in it for 20 minutes. This is just a picture to go with this main component. So now, I'd like to start the talk. Are there any questions about this picture? This is just, these are algebra words, but when you study algebraic geometry, you take algebra words and draw yellow pictures. Yes. Is it manifest? I don't think so. That's the result that we could make. I think we could make it manifest, right? Because here we have all of these parameters, right? So this is 24 parameters, but now you could start zeroing out, right? And try to go down to 9 parameters. So I haven't done that here, but the task would be, so we have 12, we're in a 12-dimensional space. This is highly over-parametrized, right? But you could think for a moment, right? So we have these 3 lines, and these 3 lines, they lie in these rulings, and Elia will easily make this manifest in the next 10 minutes. So if you ask him after the lecture, he will tell you why this is 9-dimensional, because he's an expert on lines in 3-dimensional space. Blue ones and red ones. Well, I think that's the charm of algebraic geometry, right? Geometry is in your head, right? You draw these beautiful pictures, but algebra is, harsh and unforgiving. Algebra is what we use to communicate with the computer. All right, let's start the talk. So we're discussing here determinantal varieties. So the general setup is we have parameters k and n and r. So we're going to look at a kn by kn matrix X with unknown entries I, X, I, J. And I assume that there are k by k 0 blocks along the main diagonal. The matrix is symmetric, and here, just in symbols, we have the 0 blocks. So I'm going to form the polynomial ring in these variables. And this field of complex numbers here is just to make you feel good, right? Because, of course, you cannot compute with complex numbers. This is just a feel-good symbol. So the total number of unknowns here, which I call m, this is the number of entries in a symmetric kn by kn matrix, and then I have n blocks like this that are 0. So this is the number of variables in my ring. So I'm going to study the variety V, K, N, R. So these are matrices of this shape of rank at most R. So again, n is the number of blocks. That's the number of particles. It's going to be the number of fields in cosmology. Then we're going to have k, that's the size of the blocks. That was 2. It's going to be 2 in the application. And then R is the specified rank of the matrix. So we could, for example, ask, what is V, 2, 3, 4? Okay? So 2 times 3 is 6. So we're asking for 6 by 6 matrices of rank 4. And the answer is it's this variety. The one whose dimension Elia will make manifest. Okay, here's the first theorem. Right? So in a math talk, there always has to be at least one theorem and at least one joke, and they shouldn't be the same. Right? Same old joke. So let me assume that R is in the high rank regime. So I'm going to assume that R is at least 2k plus 1. Then this variety is nice. This variety is irreducible. It's of expected dimension. So there is some number in terms of k, n, and r. It's some positive integer. And this is the dimension you would sort of expect. And that's actually the true dimension. Moreover, it's better. There are some blue adjectives that say very nice. So the minors generate the prime ideal. And in fact, the ring is Cohn-Macaulay. So it's a really, really nice situation. How does this contrast with the erratic behavior we saw in the example? Well, in the example, right, k in the example was 2. So 2 times 2 plus 1 is 5, right? So this says the good behavior kicks in if the rank is at least 5. But that, of course, here things are nice. But all of this stuff up here, all this red and blue stuff, the erratic behavior up there, was in the low rank regime. So in the low rank regime, we have all kinds of things happening. And then in the high rank regime, by which I mean R is strictly bigger than 2 times k, the rank strictly bigger than twice the block size, then the situation regularizes and our varieties become very nice. Now maybe a philosophical remark. When we got into this, so many, many papers have been written about determinantal varieties, matrices of a given rank, and that's because people love linear algebra. Who doesn't love linear algebra? So linear algebra immediately, leads to nonlinear algebra by looking at matrices of a given rank. And algebraic geometry, these are called degeneracy loci of vector bundles, but everybody and their sister loves matrices of a given rank. But it turns out that this situation with 0 blocks on the diagonal hadn't been studied in the literature. We looked very carefully, we asked everybody, so this seems to be a new theorem. Now, psychologically, why is this a new theorem? I think, in my opinion, when people look at symmetric matrices, say in applications, well, they arise in statistics as covariance matrices, or they arise in optimization, in semi-definite programming. So these matrices that arise in applications are typically real and positive definite. If you have a matrix that's real, and that means there's a lot of action on the diagonal. The diagonal is very positive, right? So therefore, somehow when people think about symmetric matrices, they think about the diagonal being filled in and big. And that's what people study. In the physics situation that we're discussing here, actually that's not true. It turns out often you have zeros on the diagonal, and I think it just hadn't been looked at from this point of view. Very good. So this is the theorem. Now already the case of block size 1 is interesting. We saw this yesterday, so let's go over this example. So if K is 1, then X is a symmetric n by n matrix that has zeros on the diagonal. So now we're looking at the variety V, N, 1, N, R. Now in this case, high rank regime means R is at least 3, right? Because K is 1 and 2K plus 1 is 3. So this is irreducible if R is equal to 3. Well, if R equals 3, it's a very interesting variety. It's known as the squared Grassmannian. It's almost as good as the totally non-negative Grassmannian. The reason is that over the real numbers, if you square a real number, it's actually a non-negative number. Okay? So there's something called the squared Grassmannian. You can find the literature. Now for R equals 0, 1, it's uninteresting, it's just the origin, but the interesting case is R equals 2, and that's the quiz. The quiz was, what is the variety V1, 4, 2? How should you approach this? Well, there's many ways to approach this, right? You can ask your smart linear algebra students. They will figure this out. Right? Or you could ask ChatGPT. ChatGPT will easily figure this out. Or you can run Macaulay 2, which we did here. Or you can intuit this, right? You can think about the matrix in some other way, right? Make it manifest. So it turns out there's 7 irreducible components. They all have codimension 3. So the Macaulay 2 code I had on the first slide, this makes this output, right? So there are 7 associated primes. So this says if A and B and D are 0, if A and B and D are 0, then C and E and F can be anything, right? And that's a 3-dimensional linear space of solutions, right? So if A and B and D are 0, and C and D and F are arbitrary, then this thing has rank 2. And then by symmetry, there are altogether 4 of these linear components, and then here's a quadratic component. So if A and F are 0, and the BCDE block has rank 1, and this matrix also has rank 2. That's the other solution. So there are 7 irreducible components, and that's the answer of the riddle as produced by Macaulay 2. But as I said, every undergrad linear algebra undergraduate student will figure this out eventually. Okay, let's summarize the situation in case 1. So the variety V1N2 has 2 to the n minus 1 minus 1 irreducible components. That's the 7. Each of them has the same codimension, n minus 1 choose 2. That's the 3. The total degree, if you add up the degrees, right, the second question you always ask every variety is, what's your degree? How curvy are you? And I think, Melissa, the Grassmann is very curvy, right? So the curviness, the degree, is counted by the number of standard Young tableaux of rectangular shape, and that's a big number, right? But here it's just 2, right? So the total degree is this almost middle binomial coefficient, 2n minus 3, choose n minus 2, and that's 10, right? The degrees are 1 plus 1 plus 1 plus 1 plus 2 plus 2 plus 2 makes 10, and the 3 by 3 minors generate the radical idea. Okay? So this is the riddle. The riddle was n equals 4, and this is for any n. All right. Let me state a stronger version of the main theorem that incorporates both the high rank regime and the low rank regime. So the dimension of our variety is equal to this number. This is some number that depends on k, n, and r, and I'm going to write L for r over 2 rounded down. Right? So in the low rank regime, and by the low rank regime I mean r is less or equal to 2k plus 2, you get this first number. Depends on r, n, and k. That's a positive integer. If r is greater or equal to 2k minus 1, you get the previous number, the one we saw 2 slides ago. Now, the second case is the nice case, and there are all kinds of adjectives in blue that say nice. And one blue way to say nice is Cohn-Macaulay. And a fun exercise is that these two formulas agree in the overlap, right? So the way I wrote the case distinction is there are 4 values of R where they overlap, namely 2k minus 1, 2k, 2k plus 1, and 2k plus 2. And it's a little exercise to show that these two numbers are actually the same in the overlap. So this requires Viennese expertise in enumerative combinatorics and playing with these. So this is a little exercise. Computer. So this requires, I don't know, A equals B or something like this. Anyway, yeah, so these numbers are the same in the overlap. Okay, so that's the theorem about dimension. There's a theorem that characterizes irreducibility. So the variety V, K, N, and R is irreducible if either R is in the high rank regime or R is odd. So if R is odd, we're also okay. It's also irreducible. Now, if R is even, it's interesting to look at the components. So if R is even in at least 4, the number of irreducible components is a power of 2 to the n minus 1. And if R is equal to 2, then it's 1 less than that. So this is, we know, the full component structure also in the low rank regime, and there's an interesting odd-even distinction. Now that odd-even, so there's a lot under the rug here that I'm not telling you, right? Because this odd-even distinction comes from the decomposability of the orthogonal N2N Grassmannian, known to some as the cosmological Grassmannian, which comes, as Lorenzo well knows, from the fact that the spinor representation breaks into 2 irreducible components when K and R is even. So all of this is under the rug here, right? I'm just stating this as a sort of basic fact about matrices and their rank. But to analyze this, you need a little bit of structure. All right, so theorems are very nice. So mathematicians like theorems, and I'm a mathematician, so I like theorems, and I like proofs of theorems. But you know what's really also fun is data. Okay, so if you're a little tired of theorems and proving them, you can always compute stuff, right? So we have explicit parameterization. So from this discussion of the orthogonal or cosmological Grassmannian, we have explicit parameterizations of all the irreducible components. Each of these components is being made manifest by some nice parametric representation, and we computed the ideals in many cases. So this is just a little chart, So for matrices, the matrix size is between 8 by 8 and 10 by 10. So here's some values of R. Here's K and N. So for example, yeah, these are bold. The bold is from the paper. So the boldface numbers are discussed in detail in the paper. So there's some discussion of these cases. So for example, if you take 10 by 10 matrices with 0 blocks of size 2, right? So there's a 10 by 10 matrix, and you have 0 blocks of size 2, and you're interested in rank at most 4, well, that's a 19-dimensional variety. The number of minors that cut this out is 19,404, and the degree, the curviness of this variety is 306,735. Now, how is this computed? Okay. A long time ago, when I was young and energetic, 20, 30 years ago, computing in algebraic geometry meant symbolic computing, and only symbolic computing. There was a, Gröbner basis engines, or whatever you can do, you run Gröbner bases. Okay. Now, what is the degree? The degree, as we know, is the number of intersection points in the intersection with the linear space of complementary dimension. And with the Gröbner basis approach, you can never compute this degree. You cannot solve a system of equations that has 300,000 solutions. Now, in the last 10 years, we've seen the advent of numerical algebraic geometry. So in addition to classical symbolic computing, now we have very efficient, reliable numerical tools. For example, the Julia package, homotopy continuation.jl. And if your number of solutions is in the order of 10,000 or 100,000, it will find the solutions with a proof, with an interval arithmetic proof obtained at the push of a button that these solutions are actually solutions, okay? So the small numbers here, like 84 and 2000, are computed symbolically, but the larger numbers are computed numerically. Very good. So in math, we have theorems, and we have computations, and our software can be either symbolic or numeric, and if it's numeric, we like it to be as reliable and as certified as possible. I have reached halftime of the lecture. I'm on slide 10. Are there any questions? Yes? No. The proof, for the proof, as I said, the proof, I mean, showing that something is prime is sort of a little bit difficult, right? You have to, so this primeness goes hand in hand with the Cohn-Macaulay property. So usually what you do is you first argue Cohn-Macaulay, and then you get prime sort of by showing that the variety is irreducible. So I would say it's sort of technical commutative algebra enhanced with a little bit of representation. Okay, very good. So now we're going to go to, now for something completely different, right? So how did we get into this? Well, the reason we got into this is because in August 2024, in Bad Honnef, near Bonn in Germany, we had the kickoff workshop of the Universe Plus collaboration. So Johannes wonderfully organized, brought us all to Bad Honnef, and we met in August 2024. So again, this is the project called Positive Geometry in Particle Physics and Cosmology. So this was shortly after, maybe a month after Daniel Baumann. So he's one of the collaborators. He's the cosmologist with his collaborators here. So they had this 4-author paper called A New Twist on Spinning ADS Correlators. And we started discussing, right? We're now in a synergy project, so we're supposed to talk to each other. And in this paper, I saw these funny spinner brackets from yesterday. So I saw all the structures that looked a little bit like the kind of thing, and we started talking, and it became more and more interesting. And then we discussed in Bad Honnef. So the theorem that I showed you 5 minutes ago, everything was completely directly an outgrowth of this conversation that we had in Bad Honnef. This was a situation where this new work in cosmology led to a new statement about matrices and their rank, and some new commutative algebra. So what is this all about? So let me say this maybe in my words. Let me take a look. We start at 9. We start at 9:30, so I have until 10:45. Okay. 35 minutes, good, great. So I will be done in 35 minutes. All right, so the setting is conformal field theory. And what I learned, so then I started talking to Daniel. This was all new to me, but he said, oh no, the foundation, this is very well known, this is in the literature. In particular, this was a useful reference. So this paper from 2011, called Spinning Conformal Correlators, but some of it, goes back to Dirac. So some of this was sort of well known. To me, everything was new, right? And anyway, so in conformal field theory, there's something called the embedding space formalism. And the embedding space formalism takes vectors in a d-dimensional space and puts them into a d plus 2-dimensional space, which I call R. So my R will be d plus 2-dimensional space. And in this larger space, we take the boundary of the Lorentz cone. Now, this boundary of the Lorentz cone, that's a quadratic surface, but we view this as a projective hypersurface. And of course, obviously, to mathematicians, if you have a d-dimensional affine space, you can identify it with the quadratic hypersurface in a projective d plus 1-dimensional space. That's what we're doing here, right? Here there's a section, so this was taken from Daniel's paper. But basically what we're saying is we're taking this d-dimensional space and we're folding it onto the projectivized ice cream cone 2 dimensions higher. Now, why do you do such a thing? Well, that makes the symmetries nicer. So downstairs in R to the D, you have a large symmetry group called the conformal group. So you have a large symmetry group called the conformal group. But upstairs, and that's an unfriendly group to me, but upstairs in the bigger space, we're a very friendly group where we just have this rotation group, the Lorentz group SO, 1, R minus 1. So under this embedding onto the cone, the symmetries have a better description. Now, in cosmology, they speak about fields, and we've been struggling, so I've been trying to understand from Claire in the last couple of months what a field actually is, so making very slow progress. So now we have n fields, and n field, each of these fields has a momentum vector pi and a collaboration, has a polarization vector wi, and I is from 1 to n. Now the assumptions, these multiply to 0 for fixed I leads to a 2n by 2n gram matrix of rank R, and this has blocks, 0 blocks of size k equal 2. So that's where our matrices come from. So the reason we looked at these matrices with 2 by 2 0 blocks is because the gram matrices here have this shape. And then we said, well, what can we say about them? I warned you already that in this talk, we're going to look at 4 different coordinate systems. The first one are just the entries of P and W. The second one, more invariant, are just the entries of the gram matrix. And what would be the Mandelstam invariant yesterday. But there are 2 more. They're going to be progressively more invariant, progressively more physical, and progressively more complicated. And here, yes. No, they satisfy relations. That's exactly that. Those are the relations. So the talk was about those relations. So the talk, okay. So this is how I got to look at matrices with zeros block on the diagonal. And I asked myself if the rank is something, what are the relations? And then went off for half a year and proved the theorem, and I presented it to you. Well, maybe I misunderstood your question. Yeah, the Xij's, so this is the ideal, they satisfy this prime ideal. The Xij are the dot products between the P's and W's, and they satisfy, these rank constraints. Are you asking, are there additional constraints? Well, R is some fixed number, so it depends on what space-time dimension is. But so the reason we got to study these things in the first place, because here in this discussion, we got to these gram matrices. Maybe I misunderstood your question. Yes. Then I get gram matrices and rank constraints. That is, okay, so that is correct. So okay. Well, yeah, no, the rank constraints come from the fact that P and W are in a vector space of a given dimension. Right? So P and W come from an R-dimensional space, and this imposes the rank constraints on the Xij matrix. But the subtlety in all of this comes from the 0 blocks. Right? So all the difficulty is exactly. Of course, if the P's and W's were to satisfy additional equations, then we would get additional, But I'm now going to go in a slightly different direction. Right? I'm still going to assume that these P's and W's are general, but I'm going to the 3rd level of coordinate system. And I warn you that now the coordinates get a little more complicated. And these are what the physicists call the well-known conformally invariant structures. All right. So conformal field theory actually considers functions on the Gram matrix that satisfy an additional invariance. Namely, we're assuming that if we shift Wi by a multiple of pi, so if we take Wi and we add a multiple of pi to it, then we're interested in functions that are also invariant under this action. Okay? And so here there are some quantities called P, H, and V. I, J, K are indices. So for example, Pi dot Pj, that's this Gram matrix entry, that's obviously invariant, right? If I shift the W, that doesn't do anything to the P, so this dot product is invariant. Now this particular 2 by 2 minor of the Gram matrix, this particular expression, is also invariant. That I call H. These are polynomial invariants. And then there is a rational function that's some other 2 by 2 minor divided by something else that also happens to be invariant. That's an invariant rational function. And in this literature, these are called the well-known conformally invariant structures. Now, this is very interesting for mathematicians such as Anna Marie and me, right? Because this is not a reductive group action, right? This is an additive group action. So Hilbert's theorem on the finite generation of the ring of polynomial invariants does not hold, right? This is now an additive group action. It's not a reductive group action. So we don't know, actually, whether the invariant ring is finally generated. We don't know much about this sort of full invariant theory. It is true, and we checked it, that these things generate the field of invariance. So the field of invariance is a finitely generated field extension, and they generate the field extension. Okay? So there's an additive group action on top of the previous happily reductive SON group action. Yes? The field is rational functions. So the ring of invariance typically is polynomials that are invariant under the group action. And by field, I mean rational functions that are invariant under the group action. And as a field, these things generate. So every rational function that's invariant is non-uniquely a rational function in these things. Alash. Okay, maybe I lied. You guys know this better than me. If we have it's the field extension. Maybe I was too quick. Even that's not clear. Okay, it's not clear. Okay, so as soon as you have a non-reductive group action, things are more complicated. In this example, they generate the field, and we don't know about the ring. Yes, Liz. Yeah, okay. We're working on it. So right now there is a very nice ongoing project by Claire and maybe Dimitri and Victoria and Nathan, I forgot. So they will then do this better. So we had a bit of a hand-wavy proof, and they promised they will write a better proof. And they're very interested in these P's and H and V's for more or less the same reason. Okay. So what I like to now do, I like to take my determinantal variety, my V2NR variety, that's the variety from the quiz, and express it in terms of this third level of coordinates. So from now on, k is equal to 2. Now this starts out pretty nicely, right? So for example, if n is 3 and r is 4, right, that was the yellow surface we've seen, then this ideal I3, 4, now in these new coordinates is simply this thing. So h12 plus v123. So they're these very friendly polynomials. Now, they don't look homogeneous, but they are homogeneous. So there's a natural grading on this, which makes these equations homogeneous. All right. So rather than having these complicated 5 by 5 minors of a 6 by 6 matrix, we just write this thing. So that's a pretty good start. So in general, let me define INR to be the ideal in a new polynomial ring of relations among these well-known conformally invariant building blocks. So now, a new variety has walked into the door, and we're going to study this variety. Right? So this variety is in have a polynomial ring, And the total number of these pi, p's, h's, and v's is 2 times n choose 2 for these two. And then here there's some symmetry on swapping j and k. We have n times n minus 1 choose 2. Okay? And INR is the ideal. So I have a ring homomorphism from this polynomial ring to the coordinate ring of my previous variety, right? And then this is the kernel of this ring homomorphism. Right? I'm going to be interested in this ideal now. Let's do another one, right? So in cosmology, we're going to be interested in R equals 5 and in D equals 3. Okay. Now, when I talk to these guys, so why are they interested in D equals 3? I thought, oh, maybe they study flatlanders. No, that's not true. They're fixing time. So they're fixing D to be 3. They're keeping the 3 space dimensions, but they're fixing time to a particularly interesting time point, and that's the time point of the hot Big Bang. Right? So we're interested here in a situation where we have 3 space dimensions, but we have a fixed time point, and that's why D is equal to 3. Now, under the embedding formalism in conformal field theory, this takes us to R equals 5, right? Because we're having the D-dimensional affine space, and we're folding it onto a quadratic hypersurface in projective 4 space, 4 being R minus 1. So for 3 fields in cosmology, we have these parameters, then the relevant ideal is I35, and then the principal ideal, this is the principal ideal, and it's generated by this expression, this thing minus that thing squared, and that is just precisely the 6 by 6 determinant. Right? So if you take this, expand the 6 by 6 determinant, and you rewrite it in these additive invariants, then you get this red expression. And this red expression is in the literature, both in Daniel's paper and also in the 2011 paper I cited. So that was pretty promising. We said, oh, that's nice. Let's now get going and let's study these ideals, and see what we can do. But it turned out to be very, very complicated. So this turned out to be harder than we thought. Now, the first question, of course, is always, what is your dimension? How many degrees of freedom do you have, right? So if the number of fields is at least 3 and R is at least 4, then this irreducible variety has dimension 2R minus 4 times n minus the dimension of the orthogonal group. So for example, if R is 5, in the cosmological situation, there's a 6n minus 10. And then we're going to use R equals 4 as a toy example. This number is 4n minus 6. Okay. So from now on, for the next 10 minutes, when I say the cosmological situation, that means R is 5. And then model case, if I say cosmology for flatlanders, that R is equal to 4. Okay, that's good. That's a dimension. But the computations turn out to be complicated. So let's, for example, look at I45. That would be 4 fields in cosmology. So here n is 4 and R is equal to 5. Now that's a 14-dimensional affine variety in C24. This number here is 24. So now I'm in a polynomial ring in 24 variables. They're called H and V and P. And this ideal, for example, contains the maximum minors of this matrix and some other thing, and many, many, many more other generators. So it turns out that these ideals are suddenly complicated. So from being encouraged, we got to be a little discouraged, right? Because we have now a new coordinate system that's more physical, that's closer to, but it turned out to be more complicated. All right. Let me take a step back. So yesterday we talked about spinor helicity. So let me tie this in with spinor helicity. So in the case R equals 4, we can go a little bit further by using spinor helicity. And this is just a beautiful side story that I want to tell you. So it turns out that our orbit space, so this is Vn4, so this is our quotient, right? So this is the variety, the affine variety that we got by taking the quotient in this field theoretic sense modulo the additive group. Right? Our orbit space now can be made manifest, that is to say, has a very nice parametric representation like this. we can write Pij just as Mandelstam variables. So Pij is just one kind of bracket ij times the other kind of bracket ij. And then the h's and the s's have similar representations. And here, the way we do this is we have a 2 by 3 n matrix of unknowns, a very long, skinny matrix with 2 rows. And then the indices, there's indices that go from 1 up to n. And then there are also barred indices that go from 1 up to n. And then if we're in the first block, we use one kind of bracket. And if we're in the second block, we use the other kind of bracket. And then there's sort of mixed expressions we're taking from the third block. This is basically an indexing scheme to talk about the 2 by 2 minors of this skinny matrix. Well, now we can actually go further. So for example, the prime ideal I54, this is 5 fields in flat lambda cosmology, is minimally generated by a bunch of things. 180 quadrics, 20 cubics, up to 156 degree 5. Now there are 50 of these variables. And this variety again has dimension 14 and degree is 10,145. So because of this parametrization, we were able to go further in the algebraic computation. But it's going to get better. Next slide is my favorite slide in the talk. It's going to get better. But before it gets better, it's going to be a bit more complicated. So I've introduced you to the 3 coordinate systems. The first one was the entries of the P and W vector. The second level were the entries of the Gram matrix. The third level were the well-known conformally invariant structures. And the fourth and highest level are the actual observables. These are 2-point functions, 3-point functions, and so on. Right? So the thing we're really interested in, the cosmologists are really interested in, are these 2-point functions, 3-point, 4-point functions. And the simplest one is this one. So hij divided by pij cubed, which is this rational function. That's one we're going to be even more interested in. Now, the way I think about this, and I'm sure this is a damn lie, but I'm saying it anyways, right? So think about it this way. So people go out there in the sky and they make measurements, right? There's like cosmic, microwave, background radio. There's a whole bunch of things happening in the sky. And the way I think about these observables is that these are things you can observe. It's not quite true, but just for mathematicians, let's think about observables, about that stuff you can observe. Okay? So let's think about these things as objects we can measure for simplicity. Okay? Now, if we do measurements, then we're in the situation of algebraic statistics. Then we have an algebraic statistical model. Namely, it's the image of our variety mapped into the highest level of coordinate system. Right? So we take one of our Gram matrices, I unravel everything. I have n choose 2 of these. So I'm mapping into a projective space of dimension n choose 2 minus 1. And the closure of the image I will call the conformal 2-point variety, CNR choose 2. So this is the variety whose points are systems of measurements for every pair ij. That's how I think about it. I'm asking, what are the algebraic relations? Maybe you don't want to make all these measurements. Maybe some measurements can be inferred from other measurements. Well, that means knowing the ideal. Now, it turns out that computing this variety is very difficult. So we don't even know the dimension. So for example, in R equals 5, the cosmological case, we believe that the dimension is 5n minus 11. Of course, the ambient space dimension is an upper bound. But we've proved this up to n equals 30 using computations, but we don't know in general. So even computing the dimension, even the most basic question, we don't know. Let's call this a conjecture. Funny minimum. And so if n is large, then so this is usually 5n minus 11, unless n is very small. This just says I had counting parameters, but then, of course, I always bound it above, by the ambient space. Okay, so that's good. Okay, so now comes my favorite slides. My favorite slide is also the last theorem of this talk. Let's look at the conformal two-point variety for R equals 4. R equals 4 is cosmology for flatlanders. So flatlanders at the time of the Big Bang. Well, it turns out that from the spinor helicity parametrization that we saw at the third level, we now get a very nice parametrization at the highest level. Namely, the two-point functions are written like this. It's a 2 by 2 minor times some other 2 by 2 minor like this. It's this rational function of degree -2 in the 2 by 2 minors of my skinny matrix. Now, whenever you see 2 by 2 minors, things are very nice. This is a G2N Grassmannian that tropicalizes to the space of phylogenetic trees. So from evolutionary biology and its fruitful interactions with combinatorial mathematics, we know a lot about G2N. The tropicalization of G2N is the space of trees. And from that, we get a whole bunch of things. So from this, we get the dimension of this two-point variety in this toy case is 3n minus 7, but we get more. So for example, from this, we see that the variety has positive codimension if n is at least 5. Let's plug in n equals 5. So if n is 5, the ambient space dimension is 9. N is 5, then 3 times 5 minus 7 is 8. Okay? So if we have 5 fields, this is a hypersurface in a 9-dimensional space. And this hypersurface has degree 270. We can compute the degree. And that we do by slicing the variety with a complementary linear space, tropically. Right? We know by tropicalizing, whenever you see 2 by 2 minors, you are ready to go. Right? You can write down in terms of trees, also known as tree-level Feynman diagram. You know a lot about the space of trees, and you can do these kind of things. Very good. So the upshot is, let me summarize. So conclusion is this project started a year and a half ago, and it started from discussions we had with cosmologists. We then took it into a pure math setting. So we were discussing for a while, and then we took it into the setting. We ended up studying symmetric matrices with 0 blocks along the diagonal. So we took the subject and we removed the context. That's what mathematicians are good at, and maybe a vice or virtue. So we can take something and remove all context and say, let's just study matrices with zeros on the diagonal. Now, then we proved some theorems, right? We understand their rank strata in terms of commutative algebra and algebraic geometry. We discovered that there's a nice high rank and low rank regime. In the high rank regime, things are nice and expected. And the low rank regime, you need lots of red nouns and blue adjectives. Now, then we went up in the hierarchy of coordinate systems. So in the third level, we ran into a little bit of a non-reductive invariant theory. And then we went all the way, we defined these conformal varieties, and we introduced them, but we found it hard to do computations. And even computing the Hilbert series, the multigraded Hilbert series of the polynomial ring in P, V, and H, is a very interesting and challenging problem, currently investigated by the team I mentioned. Now, these varieties, if we were to understand them, they would govern the relations among the two-point functions. And if the world were as naive as I made it sound, this would give us the relations among observables, which in my naive mind are things that you can observe. Good. So let's end on a homework. Removing all context, let's say nothing in this talk made any sense, and you just entered the room, you could still look at this 6 by 6 matrix. And you could ask, look at the 5 by 5 minors. What is the variety defined by the 5 by 5 minors? What can we say about the matrices like this of rank 4? This has some dimension. Maybe Leah will explain to us why. And with that, I thank for your attention.